Something I've always felt when learning math was the severe lack of explanations for its basics. The basics that you only learn in university or after making many mistakes to the point that experience fills the gap. Even at that point, the teachers and professors aren't willing or able to explain their process in words. And online videos don't cover a wide range of basics to enable someone without any math education to start learning in a compact and coherent way. But here I will combine my experiences and provide a comprehensive overview of math and how to get started as a beginner with 3 simple concepts. Concept 1 is numbers. Math exists because counting exists. If you can count, you're already 1 of 3 steps done. When you don't count or have numbers, you have no math to do. Here's a simple example with a black screen. If I turn the background to a different color, now you can see the black circles because there's a distinction. If I turn the screen back to black, then you can't count anything because everything is black. This is the most basic form of mathematics, to be able to make simple distinctions and recognize the difference between two things. Actually, this doesn't just apply to math, but everything you do in your life. You can tell the difference between 2 sounds, 2 tastes, 2 smells, 2 people, 2 feelings. Anything you do in your life is basically an automatic counting, and that's where math starts. So anything you perceive through your senses can theoretically be put into math because you can count, label, and distinguish between differences. The only limitation then would be your imagination. Just as a writer or artist may take months to write a book or create an artwork or animation, someone using math as an outlet needs the same level of attention to detail in order to come up with an equation. But to get to equations, we need another step, which leads to the second concept of arithmetic. Here, we can manipulate numbers in 3 ways: make them bigger, smaller, or convert them. To do this, we are introduced with a few easy-to-remember symbols that can also be put into pairs, and which you may know as adding and subtracting, multiplying and dividing, and power and roots. There is also exponentiation and logarithms and trigonometry symbols like sine, cosine, tangent, and their inverses, but they don't necessarily increase or decrease a number, and they are like different scales of measurement. Trigonometry, for example, measures things going around in a circle instead of a straight line, so I won't be talking about it because it's a different way of looking at numbers. All I will say is, any software or practical application that requires something to rotate, repeat a cycle, or deals with triangles and angles has some element of trigonometry in it. As you can see in the animation, it may look like the line in the circle is going around, but if we translate the height into the straight line you see in the middle, the dot goes from +1 to -1 and will repeat as long as the rotation continues. Back to the 3 ways to manipulate numbers, let's talk about conversion. This concept only exists when applying math in the world, such as for measuring things like temperature and distance. Conversion in most cases is done with multiplication, for example with distance in inches and centimeters. But for converting temperature from Celsius to Fahrenheit, it includes both multiplication and addition. So when 2 different numbers point to the same sensation, that is conversion. So now you've learned that each arithmetic symbol serves one purpose, one function. And if you want to increase or decrease a number a certain way, you can always look up all these symbols online and you will find the one you need. Or it may be necessary to combine them in order to do something specific, which brings us to the third and final concept, algebra. Algebra forces you to label things more specifically. For example, you can count the number of shapes or objects on the screen and it would be 6. But now I ask you to count each kind of shape. You say there's 3 circles, 1 square, and 2 triangles. What this means is everything is labeled and counted differently. When you hear the word shape, you have an idea of what the word shape means. When you hear circle or square, you know to only count those types of shapes. This labeling is important in algebra, especially when you turn what you see on screen into an equation and change the labels to letters. In math and science, things, concepts, and ideas are labeled as letters called variables. This is because it is simple, easy to read, and saves space on paper and screen. The downside to labeling things as X, Y, and Z is that you need to remember what they are referring to. For example, if you are in theoretical physics, the letters could mean subatomic particles, If you are in psychology, it could mean people with specific traits. If you are in biology, cells, engineering, stress and strain. Go into any field and they would all have different definitions for X, Y, and Z. Obviously, they use other letters and symbols, but the point is that you need to know what you are reading and labeling when you get into algebra. So that is the first new thing you are introduced to, variables. The second and last new thing you learn is the equal sign. It separates numbers to two sides, forming what is called an equation. So remember that each letter represents a different shape? If you add them all up, they equal 6. So what does this mean? Let's say you have a bag and you put 6 things inside the bag. The bag represents the equation, the whole system, the whole category by creating a space that is separate from everything else. All we are looking at now is everything in this new space, in this bag. We ignore everything outside the boundaries of the bag. If I say there are 12 shapes outside, you should not care because all you should be looking at are the 6 shapes inside the bag. Why do I say boundaries? Because similar to artists, when you tell them to draw a human, they already know that a human has a head, chest, arms, legs, and many other parts. You tell a mathematician or anyone with advanced knowledge in math, and they would be able to turn whatever you are talking about into symbols, numbers, and equations. Obviously, you can't do everything with math, just as an artist can't draw music, because both of these people are limited in the medium they are expressing themselves in. So within the boundaries, we have 6 objects, which we can write in the equation. It can be on the left or right side, it doesn't matter where you write it. On the other side of the equation is where you break down the total number into its constituents, or the parts that would add back up to the whole. This is a simple way to build any equation. One side represents the total value, while the other side represents all its different parts. Taking the previous example, we had 1 square and 2 triangles. Y represents the number of squares and Z represents the number of triangles. To find X, or the number of circles, we can add 1 and 2 to get 3, and it is easy to guess that we have 3 missing shapes. Add everything up and the left side of the equation equals the right side. But that is too easy, so let's make it a bit more difficult. Say we have 27 total shapes in the bag. Now everything on the left side must add up to the right side. Can you guess how many of each shape exists in the bag? You can't because it's impossible. What if there's 10 squares in the bag? Again, you can't. And 4 circles? So now you can add the numbers on the left and guess the number to be 13. But instead, let's subtract and move 14 to the other side. But hold on, why do we move the number to the other side and change it from positive to negative? This is where a hidden rule in algebra isn't taught and what I call the conservation of numbers. You aren't creating numbers out of thin air or removing them. Using the bag analogy, you are not putting more shapes inside or taking them out of the bag. The bag is still closed and there are still 27 shapes inside. What you are doing to the equation is, you are finding out what Z is or how many triangles there are. You can say this is a shift in focus because instead of focusing on the total number of shapes, now you only care about the number of triangles. Just as how the right side had the total number and the left side had the parts, now the roles switch and Z is acting as the total number. Because of this, we need to move everything to the other side of the equation because now they act as parts. Again, it doesn't matter if the total number is on the left or right side of the equation. You can switch the total number and its parts, but issues arise when moving the parts to the other side. Because when you do that, you have to do the opposite arithmetic operation. Here, we have positive 14, so we are adding. To move it to the other side of the equation, you subtract, which is the opposite of addition, making it 0 on the left, because 14 minus 14 is 0, and subtracting 14 on the right. Again, you are not adding or removing numbers out of magic. You are still playing with the parts inside the bag. It is a mental reframing, a different visualization, and a different focus you are doing. So to finish, you subtract 27 with 14, and now you have the number of triangles. This process of moving a number to the other side with the opposite operation works with all arithmetic symbols: addition, subtraction, multiplication, division, power, roots, and more. You can refer back to the arithmetic section to see all the opposites, but essentially once you get over the two hurdles of unknown variables and the equal sign, algebra is all about balancing out everything with opposites. And as you may have seen through other forms of media, equations can get really complex using simple arithmetic. So if you understand the purpose of equations, which is again balancing numbers, then you know there is always a positive and negative operation, an increasing and decreasing operation, a forward and backward operation, or whatever dual concept you want to use. It doesn't matter what you label it, there is always an opposite to make sure the other can be balanced out. So how do you use these fundamentals? Whenever you are struggling or studying too hard and everything takes too much effort, return to these three simple concepts. Step 1, can you count? Can you tell the difference between two things? You count your fingers, you can hear different sounds, maybe you see different colors and shapes, then that's good. Now for step 2, do you remember 8 or more arithmetic symbols? And do you understand how to use them properly? Do you know how to add, subtract, and divide and multiply? Okay, you made sure that you didn't forget anything, so arithmetic is not the issue. Step 3, do you understand what the variables and equal sign mean in algebra? Do you understand why you move numbers to the other side or why you write the equation a certain way? Once you understand that, you should have no issue with about 90% of mathematics. The rest are specialized areas with more definitions and details you need to remember, which you can learn more effectively when you're applying the math in those fields. If you have a great understanding of these three concepts, numbers and arithmetic and algebra, and you are still having trouble, then all that means is you are learning something new and that new topic is not explained in a way that makes sense to you. This is your time to ask specific questions online or to a teacher and have them reframe it in a way that makes sense. Unfortunately, not a lot of people can explain math in simple terms and they may resort to using jargon. So how do you know if you understood a math concept? If you still don't know something in your bones, in the core of who you are, then you still don't know it. All questions must die when you have understood something completely. Don't lie to yourself about the questions you have. Ask a question that truly hits the core of your confusion. Otherwise, you will go on and on learning about more math without even understanding how to count, and that's not a good place to be when you've learned math for over half your life. But then again, you might not like the way I present information or the way I explain things, and that's good because you might find someone else that explains things in a way you are more receptive to. So after you return to these three steps every time you struggle with math, it will become automatic and you won't have to remember anything anymore. Of course, this video mainly covers algebra and not geometry and other aspects of math, but the same thought process can be applied anywhere along your math journey. So this is math. It's all about recognizing patterns in the world and mapping it into symbols that we as humans made up. You can do this formally through mathematical notation, such as through equations, graphs, and geometry, or you can do this informally, where you make up your own symbols and language and rules besides the ones I mentioned. The informal method is more freeform and more for personal use because you can't communicate it to other people. It's like creating your own language. It is also for you if you have your own intuition of how to craft a mathematical language, or if you trust that you can rebuild any formal equation in your own way. But if you want to work with other people, then a formal approach is more fitting, since it is internationally consistent and well known. The best example of formal application is through your phone or computer. Nearly everything you see on your screen is deliberate mathematics. Even the tiny pixels are light calculations made many times each second, and you can bet someone thought about how to do it when they first created it. Every keystroke, every tap on your keyboard, every image that is moving or not moving, every color, and even your finger touching the screen, all comes from people who have thought about it through some sort of mathematical context. This is because they were able to recognize a pattern in how colors and light and everything works to be able to miniaturize it into a small electronic system. So if you ever draw something on a computer or phone, you can be assured that it is math doing all the work to make your colors and lines and brushes. And you see this as a blatant example with AI art. When long ago people thought art and math were separate, any person with a deep understanding of math knows that almost anything can be put into math. So don't be surprised when a few years or a decade or so later, videos, music, graphic design, voice acting, singing, writing, movies, animation, and any and all forms of entertainment will likely be automated. Within the limitations of engineering, it can also be applied to the medical field, to robotics, or to anything that has been put into a computer. It's even likely that math would begin to write itself, all because of a deep understanding of math and its applications.